Hello, welcome. Let's try to solve another Leetcode problem 780 written points. So for this problem, we are giving four integers sx and sy, tx and ty. So we're going to return true if it is possible to convert the point sx, sy to the point tx and ty through some operations. Otherwise, we're going to return false. So the operation is going to be x plus y, or x plus y and y. So let's just use an example to understand all operations. So for example, this is sx and sy, it is 1, 1, and we are going to check if we can reach tx and ty. Yeah, let's just check. So for example, we can use this is 1, and the second place is going to be this one plus this one, it's going to be 2. Now let's just check next one, maybe for the next one. So this is 1. We're going to update this one to 1 plus 2. So it can be updated to 3. And this is still 2. So what about the next one? So for this is 3, it is okay. And for this 2, 2 going to plus 3, it's going to become 5. So this means we can reach 3 5. Yeah, this is okay. So we're going to return true. But how many operations? Of course, this is going to be a BFS. So for each of the time, we're going to have 2 paths, and for each of the number, we have 2 paths, and there are going to be a lot of different paths, and definitely it's going to be time limit exceeded or memory limit exceeded. Let's just use an example to check why it didn't work. Yeah. So let me just check the first example. So actually, this is the code. As we can see, if we use the BFS, definitely it didn't work. It can pass some testing cases, but it cannot pass all testing cases because, yeah, this is just a brute force. Normally, this brute force cannot solve such kind of hard problem. As you can see, we're gonna have memory exceeded. Now we're gonna try to use another idea to solve the problem. So the idea is mod. So instead of reaching from the starting point to the ending point, so we're gonna go backward. So we're going to reach from the ending point. So this is going to be 3 and 5. We're going to use this 3, 5 to reach the starting point 1 and 1. But while we are reaching the point, we don't need to minus 1 by 1 until we reach the final point. So for example, for this number, 5 is bigger than 3. So this means for the next number, we're going to update this 5. So 5 is going to be updated to 5 minus 3, because here it is plus, but here it's going to be minus. So the number is going to be updated to 3 and 2. Yeah. So if we just use plus and minus, so here we're going to use minus. So for the next point, this is 3 going to be updated to 1 and 2, because 3 minus 2, because 3 is bigger, 3 minus 2, it is 1. And the next we're going to update this 1 and 2. So for this 1 and 2, this is 1, this is 2, 2 minus 1, it is 1. So finally, we get 1 and 1. So how many operations? So there are going to be a lot of operations. Definitely, this is also a brute force. But we can use another way. We can use the modular to make the number smaller. Yeah, because, this is 3, this is 5, it is okay. But if this number is bigger, definitely we want to make this number smaller. Yeah, because let's just use an example. So for example, our starting point is 5 and 5. And our destination point is going to be 5 and 50. What are we going to do? We don't need to minus 50 every time. So it's going to be 10 times or 9 times until we get this point 5 and 5. So we can directly use the modular to make it smaller. Because anyway, if this number is bigger, we want to make it smaller. How can we make it smaller? We can directly use modular, right? So here is just the same idea. So here, if we want to use formula, use modular, because this 5 is the same as this 5. Definitely, we don't need to use it, because if we use modular 50 to 5, it's going to be 0. But our final number can never be 0, because this sx and sy going to always be more than 0. Let's just check that. So yeah, as we can see, all the points are going to be positive numbers. This means we cannot do that directly. Let me just find. Yeah. So this is just a special case. So if sx equals to the tx, So definitely we can directly calculate it. So the calculation gonna be this 50 minus 5, it's gonna be 45. 45 modulo 5, it is 0. So this means it is possible. So this is just a stencil case. But what about our case? So yeah. So our case is yeah. Let me just use the first example. Yeah. So our case is 3, 5. We're gonna use the 3, 5 to reach 1 and 1. But how can we reach that? We're gonna use the modular. So the first step is gonna be this is a 3. This is okay. This is bigger. So we're gonna use a modular. So 5 modular 3 is gonna be 2. It is okay. So what about the next step? So 3 is bigger. 3 modular 2 is gonna be 1, and here it's gonna be still 2. Yeah. So up to now, as we can see, we reduced a lot of calculations. Before it is 4 steps. Now we only have 3 steps. So after 3 steps, we can compare directly. We can compare this 1, 1, and 1, 2. If this 1 equals to this 1, this is okay. We only need to compare the second number, this 2. So this 2 minus 1, it is 1. 1 modular 1, it is 0. This means it is possible. Yeah, because this 1 and 1, they are equal. This 2 and 1, we just need to compare how many minors, but we don't need to do that. We can directly use a modular. So 2 minus 1, modular 1 equal to 0, it means it is possible. Yeah, so everything is just about mathematics. Yeah. Now let's just use this idea to solve the problem. So from the beginning, as x, if while as x less than tx, and as y less than ty, and tx should not equal to ty. This is just a stencil case, because you know if tx equal to ty. So for example, this is x, sx, and sy, 1 and 1. So if they are equal, so for example 50 and 50, and maybe 80 and 80, is that possible? Definitely it is not possible, because if we are starting from 1, 1, next it will be 1, 2, or 2, 3. It can never be equal. So this is why we're gonna check. They must not equal. Yeah. Now we're gonna use the modular to check. So we're gonna use if tx, we just need to reduce the tx by using the modular. If tx is less than ty, ty modular equal tx. So else it is another case, tx more than ty. So it's going to be tx modular equal to ty. Now we should know that tx and ty have already been reduced to a smaller number. We can directly check that. Yeah, we can check if tx equal to sx and ty equal to sy. So we're gonna return true. Yeah. So the second case is if tx equal to sx and yeah. Let me check. Yeah. So the second case is if tx equal to sx, but what about ty is more than tx? What's gonna happen? So we can directly return ty. Yeah, I think I did something wrong. This is tx and sx. This is ty and sy. Yeah. Yeah, because if they are equal, we're gonna stop the while loop. But this ty can still be bigger than tx. If it is smaller, definitely it is not possible. So we're gonna return false. If this ty still more than sy, so this ty gonna minus sy. And we're gonna modular tx equal to 0. Yeah. So another case is let me just maybe copy or not. If ty equal to sy and tx more than sx, so we're gonna return the similar things. So it's gonna be tx minus sx modular. Yeah, modular this ty equal to 0. Yeah. So this is all the cases. Otherwise, so we're gonna return a false. Yeah. So this is the whole idea about this problem. Yeah. So instead of reaching from the starting point to the ending point, we're gonna reach from the ending point to the start point. because in this way, we can directly use the modular to make the number smaller. So after making the number smaller, we can directly compare. If they're equal, it is okay, we're gonna return true. If tx equal to sx, definitely we're gonna compare ty. If ty equal to sy, definitely we're gonna compare tx. Yeah, right. Otherwise, we're gonna return false. Now let me just run it to check. As you can see, it works. Now let me submit it. As you can see, it passed all testing cases, and it's pretty fast because this is the best way and maybe the only way to solve this problem. Thank you for watching. See you next time.